Hi, my name is Alan Ward. This is my machine learning final project uh, titled Pneumonia Diagnostic Model. I decided on this project to address a particular learning problem, um, which is one of the deadliest issues in healthcare, pneumonia. Pneumonia is an infection that inflames the air sacs in one or either of your lungs. It will fill the sacs with fluid or pus, causing coughing, fevers, chills, and difficulty breathing. Pneumonia can be bacterial, viral, or fungal, um, and it's not only very deadly but also extremely common, as pneumonia is responsible for upwards of 3 million deaths every year and is currently the fifth largest disease worldwide. Problem with pneumonia is that many symptoms of it are similar to other common illnesses, and so it's often ignored or misdiagnosed until it's uh, too bad to cure. So the problem I'm trying to solve is to see if machine learning can be used to diagnose pneumonia, thus quickening the detection process and saving as many lives as possible. To do this, I found a data set off of Kaggle with about 6,000 lung x-ray images. The images contained either pneumonia or healthy lungs, and with that I was planning to train the AI models. So I'll walk you through the steps of how I decided on the models, I trained them, I'll show you the architecture, I'll talk to you about the data augmentation I used and the techniques, and hopefully we'll both be able to gain an insight on how to detect pneumonia. So the first model I used was the VGG16 copy, or a copy of the VGG16 model. Now I found that on a paper that I've linked in my slideshow while I was looking for models that were good at classifying images with small data sets. Now this model is very large. It consists of 13 convolutional layers and 3 dense layers and has an approximate parameter count of 138 million. It took about 10 hours to train the model over 5 epochs, and even though the model loss value was very, very, very low, the accuracy was unfortunately only about 62%. So what I, deducted from that was that the model was being overfit, or it was overfitting the data. So this means that the model was memorizing the training data instead of learning the patterns, which means it can perform very well while training, but when testing with new data, it performs quite poorly. So to fix this problem, I did two things. One, I used data augmentation to increase the data set, increase the variation in the data set. And two, I used smaller models to, one, avoid overfitting, and two, also speed up the rate of training. So I did very simple data augmentation. I would rotate, shift, and zoom into each of the images, and I duplicated the data set in that way to triple it from about 5,000 for the training data set to 15,000. With that augmented data set, I started with a very simple linear classification model. It had roughly 100,000 parameters, and after training it for less than an hour on 8 epochs, it came out to about 77% accuracy. After that, I trained a multi-layer perceptron model with the same augmented data set. This model has 2 dense layers, one with 100 inputs and one with 50. It has about 5 million parameters in total, and the model trained for a bit longer than the linear model, also with 8 epochs, and also achieved roughly 77% accuracy. After that, I moved on to a CNN model. I know that those models are better suited for image recognition. So the CNN has 1 convolutional layer and 2 dense layers. with a parameter count a bit over the MLP model, about 6 million, and it took a bit longer to train as well, but it actually had almost exactly the same amount of accuracy, 77%, just like the last two models, which is a little unfortunate. So after some more research, I came upon the ResNet 18 model, which is said to be very good for, again, very good for small data sets like this one. So I used the pre-trained model off of the torchvision.model library, and I modified it because the X-rays are only have one channel. They're like grayscaled, as opposed to like the 3 channels for RGB values. So the ResNet had almost 12 million parameters. It took about 5 hours, again over 8 epochs, but the final accuracy was 90%, which was far better than all the other ones, which I was quite happy about. Now, to apply this research, there's a lot of room for improvement. There's other techniques I could continue using. I could try augmenting the data a bit more. I could manipulate the parameters or add some more convolutional layers, but it's clearly shown that the model could play a part in assisting the diagnosis of pneumonia through medical imaging. Let's say the model was integrated some way into the X-ray machinery or the software that they use in hospitals. It would be able to flag images that it detected pneumonia in, which would give possibly those images a priority look for doctors and could quicken the rate of diagnosis, which even if you're diagnosed only a couple hours earlier, that could increase your odds of survival. And scaling that to 3 million people are dying a year, that could save countless lives. This project brought a lot of insight into the architecture of machine learning, how they work, or machine learning models, how they work, how to construct them, how to apply them to different industries, in particular the medical industry, and strategies for just improving the accuracy. I had a lot of fun with this project, and if it had been given a much larger scope, say a PhD thesis, it'd be interesting to see how I could apply this to real case medical processes and see how professionals would benefit from working with these models. And I'll just do a slight demonstration for the ResNet model, just applying it to 16 images for easy visualization. You can see that it messed up on the first 2 of the first 4, but out of the 16 I got 14 correct. So not perfect, but it's clear to see how this could be very beneficial to medical diagnosis. So thank you for watching, and I hope you enjoyed.